We're together today for a session on electricity tariffs. So I just introduced myself. I have a PhD in applied economics on the regulation of the gas transport system, and I'm currently working at the French distribution company entities. So the first paper will be presented by Mohammad Ansarin from the Rotterdam School of Management and at Erasmus University, and will be about the effect of distributed generation on the efficiency of different kinds of electricity tariffs. Then we'll go on to Carine Staropoli on a paper about the perceived price complexity of electricity and water tariffs with a behavioral economics experiment. And finally, we'll go to you, Claudia Günther, for a paper titled Prosumage of Solar Electricity, Tariff Design, Capacity Investments, and Power System Effects. So we have an hour and 45 minutes. I think it makes about 35 minutes per each of you. You can choose to last a little longer or have a shorter presentation for letting more space to questions. That's up to you. So Mohammad, if you want to start, it's your.
Yes, thanks, Florian. Let me just try to share my screen here. Okay, can you see the slides? Great.
Yes.
So thank you, everyone, for joining in this talk about economic inefficiencies of pricing distributed generation under novel tariff designs. So I'm going to be presenting today some preliminary work that I'm doing together with Yashar from the Rotterdam School of Management, and also Wolfgang Ketter, who's from the University of Cologne, and John Collins from the University of Minnesota. Since this is kind of preliminary work, please don't feel hesitant about like suggesting any changes in the methodology even, or any other like sensitivity analysis that might be needed, because those will definitely come in handy. So I don't think this slide would come as a surprise to anybody here. I think we're all well aware that the amount of solar photovoltaic capacity around the world has been increasing dramatically in the past years. And it doesn't show any sign of stopping, at least not at the global level. Particularly at the residential scale, we're seeing a huge growth in electricity because more and more regions are experiencing cost decreases. For example, in the United States, costs have been decreasing all in the past few years. And this has led to more and more places finding that electricity costs are, solar PV costs are low enough that it is a viable alternative to other means of procuring electricity. Now, electricity costs generally consist of multiple components. There are some soft costs, there are some costs that generally depend on the size of the solar installation, and there are some that don't depend on the size of the solar installation. So I'm going to first start by considering this and comparing it to the revenue from solar photovoltaics. Basically, these costs that I just mentioned, we can kind of consider it as like a line like this with an intercept. It's basically defined with two parameters, right? We have C0 and CG, which is the intercept and the slope respectively. This kind of reflects the previous slide I showed with module costs being dependent on per module's prices and also an overall installation price. Now, when a household chooses to install electricity, it's usually because there's some benefit to them. And that's usually the amount of money that they're getting back from selling that electricity or offsetting the electricity that they were already buying. Over the time span of the solar panels installation, we can kind of imagine that as being dependent on the installed size of the solar panel. And that kind of also is increasing linearly as the size of the solar panel installation increases. there's going to be a place where these two intersect, which is the first capacity at which it's usually good for the household to buy electricity, to buy solar photovoltaics. Usually, however, most places we witness a curve that's more like this. The value of the solar panels is so low that it never actually intersects with the cost curve, so households never choose to buy it. That's why most policymakers have been trying to do one of two things to make the case more viable for more households. They've either been trying to decrease CG, the slope, or C0, the intercept, so that the curve, the blue curve, starts intersecting with the red curve more often. And sometimes they're also adjusting the red one, the red line, the future revenue of the household. And they're trying to push that more and more towards a higher slope so that it intersects with more and more households. So the more and more households intersect in their with the cost profile of solar panels. Now, here we're going to focus on the difference in cost when tariff changes, where the red line moves basically, because the main thing that defines the slope of the red line is basically the household's characteristics, which is something that policymakers are going to have a very hard time changing if they can at all, and the tariff that is used to price the electricity, which policymakers have pretty much a free hand in. Now, to understand the economic consequences of this, we're going to kind of consider where these intersects happen, where the generation sizes actually are, and use those to calculate the differences in costs between these. We can imagine that one of the tariffs is going to be akin to the real value of electricity at any given time. And the other tariff is going to actually be the tariff value, which is always going to be a little bit different from what the real value of electricity is going to be. The difference in installation size and consequently the difference in cost are going to give us some measure of social welfare loss because of the installation of solar panels that are not sized according to the real value of electricity. For the real value of electricity, we're going to consider, let me clear all the drawings quickly. We're going to consider the value of solar methodology, which we can generally divide into three pieces. The first is the real value of electricity at any given time, which is the energy itself. For example, we can consider wholesale market prices for this purpose, which do show a very large variation in different minutes even for the price of electricity. The second factor would be anything that causes reduction in grid costs, grid operation costs. I'm using grid operation costs here very loosely because I want to also refer not just to the transmission system operator and distribution system operators, operations and maintenance costs, but also any kind of line losses or regulation, voltage or regulation benefits that will come from solar panel installation. And also, there might be other cost factors that are being reduced for the TSO or DSO, which I also want to bundle into this second one. And the third one is the value of clean electricity generation, which you can kind of think of as internalizing the externalized benefits of clean electricity generation. Now, this real value of electricity, because of its complexity, first of all, and also because of how it works, it will always be somewhat different to the tariff that is used for pricing the solar panels electricity. The most common option used in many places is either a flat option, a buy all sell all option, also called that, which is just a single per kilowatt hour price and is a current default rate from the data set that we're using. Or a net metering option, which you can call a net purchase and sale, where there's a single price for self-consumption, which is equal to the retail price. And then there's a real-time, or let's say a worst price for sale. Here we're considering a real-time price. We're also assuming that we're also looking at some in-between options, you can say, where there's where the self-consumption accumulates over a time window. which means that users have more and more time to basically accumulate that solar energy for their own consumption rather than for selling to the grid at a worse price. This is, we've considered a day, a week, a month, and a year to kind of simulate the different time spans, the different variabilities that we see in solar generation patterns, and also to mirror what we see in the real world in terms of what policymakers choose. And of course, we're going to use this to compare to the real value of electricity, which for the first thing, we're going to consider locational marginal prices from an ISO, from an independent system operator at the node that we have. And we're going to consider the capacity value of the solar panels' electricity generation. And then we're going to also consider returns from renewable energy certificates that are sold by the utility that is gathering all this clean energy and selling it away for these certificates. To run the study, we're using data from multiple different sources. We have data generally from Austin, Texas, and from 2016. And these are from multiple sources. The first is ERCOT, the Electricity Reliability Council of Texas. And we're using real-time locational marginal prices from their Austin, Texas load zone. We're also going to be using some value of solar rates and retail rates from Austin Energy, the local public utility, excuse me. And on the electricity side of things, we're going to be using Pecan Street Data Ports data from about per minute household solar generation and installation data. We managed to clean and prepare data for about 125 households here. However, this data set doesn't exactly include cost, so we don't know how much those solar panels that are installed cost, even though we know their size. So we're going to use data from the Austin Energy Residential Solar Incentive Program, which is also pre-2016, to basically append the Pecan Street data so that we also have cost data as well. This data set has thousands of households' costs and installation information in Austin's in the city of Austin's region. And as you can see, the data varies quite dramatically, but two things I want to mention here is that we can clearly see a pattern of linear increase and variation for each of these, for each household, for each year, if you will. And the second thing I want to mention is that I've removed data from 2010 and 2015 because there were some irregularities that couldn't be removed. And so I had to not use those data points. Well, with this data set, we can clearly find C0 and CG, the slope and the intercept of the cost curve. And then we can calculate different generation sizes for different tariffs. And with that, we can kind of compare the different generation sizes of the tariffs. First, we're going to compare the generation size of the flat tariff with the generation size if these households were receiving the real value of their electricity. In this slide and any future slides I show here, the black line is going to be for the tariff, and the black dots are going to be for the tariff, and the yellow dots are going to be for the real value of electricity. As you can see, the differences are not too stark here because the flat tariff is already designed on a value of solar basis, and it gets values that are kind of close to, in generation size, to the to the real value of electricity. Now, some households have larger changes in their solar panel generation size, so they end up with probably larger efficiency losses. Now, if we sort efficiency loss from lowest to highest, we can get a curve like this for the households. We can see that a few households have very high efficiency loss, but most households have a relatively low value. By relative, I mean what you'll see in future slides when we compare against net metering, which was very high values. Now, if we consider net metering and contrast the flat tariff with a net metering tariff, we see that a net metering tariff finds almost no households install solar panels because it is no longer worth it. This is mainly because that second value component about grid operation costs is no longer factored in. So most of the households, except for one or two, which install far larger solar panels than they used to, most of them don't really install solar panels anymore, which of course creates a lot of efficiency loss. However, this efficiency loss gets gradually reduced if we add accumulation. And as the accumulation becomes a larger amount, the generation, more and more households choose to install solar panels. So this is for net metering with daily accumulation. And you can see that already many households choose to install solar panels. This is with weekly, and as you can see, a few more households have chosen to install solar panels. And as we move on to monthly and then to yearly, we see that the amount of solar panels being installed increases further and further. And likewise, if we look at the profile of the efficiency loss, we can see that initially the curve is quite similar to what we saw for the regular net metering, and slowly it becomes more and more similar to the flat rate because the efficiency loss decreases more and more. You can think of this part of the curve being pushed further and further to the right. In the end, we have a situation where the curve is pretty similar to the flat rate, except for a few tariffs, except for, sorry, a few households which are responsible for the vast majority of the efficiency loss. Now, we did two sensitivity analyses on these results. First of all, we checked what if the second value component about grid operation cost capacity value for the tariff, for the retailer. What if this was lower or higher than this 5.9 cents per kilowatt hour, which we calculated here? So you can imagine the second value component would drastically differ based on where we're installing the tariffs. It might even be negative for many places. But here we're just changing it 10% compared to its original value in this region to see what the effect is going to be on the total efficiency loss. You can imagine total efficiency loss is like the area under the curve of those sorted data points that I showed you earlier. We're going to also be talking mainly in relative terms here because of the household count. So as we can see, as we increase this value of the second value component, generally speaking, we see that for every tariff, the total efficiency loss decreases. The differences between tariffs, though, it kind of stays the same. There are three countervailing effects here. So when the extra credit decreases, so when it goes closer and closer to zero, first of all, households need to install larger distributed generation installations so that they can have feasible solar panel installations, like economically feasible, if you will. On the other, in addition, a few households find it economically and physically feasible to install solar panels when they credit the real value of the electricity generation, but they don't if they're credited according to a tariff. Both of these effects cause a lot of inefficiency increase. So more efficiency loss. But there's an effect that counteracts this where fewer households can achieve a feasible DG installation, distributed generation installation, both when they are credited the real value of their generation and when they are credited the tariff value. You can kind of imagine them as kind of leaving the market entirely. And that means that the total efficiency loss would decrease. These three effects are generally dominated by the first two, which cause an increase in the efficiency loss as the value component decreases. But sometimes they are also overwhelmed by the number of houses that are leaving the group entirely and causing a decrease in the efficiency loss. So generally, however, we see a decrease. A second sensitivity analysis that we did was about what if the solar panel installation costs, so C0 and CG, were to change, because this is obviously something that's changing a lot, and And we really would care what we would see if the C0 CG value were changed by about 10%. This can you can not just imagine this as like cost decreases on a per year basis or a differences in cost compared to what we calculated, but also if if an incentive program stepped in and changed these costs. We want to know what the total efficiency loss will be. So we consider these costs and we see how how total efficiency loss changes per tariff. And we see, first of all, that for C0, for the intercept, the changes are quite small. So compared to what we saw earlier for the second value component, we see that there are very minor decreases for increases in C0. However, for CG, we see that there's an increase, and the increase is more pronounced. So this is expected because they're kind of directly related, the amount of CG and the location at which that point on the curve actually intersect, which means that we're going to basically expect to see this effect. And if we talk, and I'm also not going to talk about things on a per tariff basis because that can get, there's a lot of like intricate details here that I can mention, but here on a counterclockwise from top right, we have the flat tariff here. Where is there? We have the flat tariff here. We have net metering here. And then we have net metering plus daily accumulation on this one. Net metering plus weekly on this one. Net metering plus monthly accumulation here. And net metering plus yearly accumulation here. And as you can see, they vary in different ways, and their loss values are also a little bit different. So to conclude, the flat rate price, which is the value of solar price in Austin Energy, it has small inefficiencies, especially when we compare it to the net metering scenario, which has very large inefficiencies. This is mainly because most households on the net metering choose to forego solar panels because they're just not economically viable anymore. Also, allowing for accumulation over long time windows, it increases solar panel uptake and reduces inefficiency. Net metering with yearly accumulation is pretty similar to a flat rate tariff in terms of overall efficiency loss. Economic inefficiency, we also see, is strongly tied to the second value component. It generally decreases as grid operation costs decrease further and more panels are basically added to the grid. But it is less dependent on the original price of solar panel installations. It does decrease with increasing fixed costs and increase far strongly with increasing variable costs, however. Now, for future work, we plan to change this model in a few ways. One thing that I'm still grappling with, and is really the biggest question I have here, is we're very good here at understanding when one of the people who have already installed solar panels in our data set is leaving, so is choosing no longer to install solar panels. But we're kind of puzzled right now by how to basically add in potential installers for that we don't see, that we don't capture in our data set. So if we, to phrase it differently, if we decrease the price, there are going to be more people installing solar panels, but we don't know how to account for this increase in solar panel installations because they also represent some inefficiency. We're also considering comparing these tariffs with other subsidy schemes such as tax incentives, tax rebates, or subsidies that are only based on the size of the installation, if you will. Are there other things that we mentioned, and are there other things that you think will be interesting to study here? Please let me know. I'm very excited to hear what you think about this study. I look forward to talking with you about it.
Thank you very much for your presentation. The floor is open to question. Feel free, the other speakers or attendees to ask us some questions. You can also use the chat window if you prefer. Anything is fine. So maybe I'll start with a question. You calculate the tariffs as to be cost efficient for the utility. Do you have any comment on the fact that the tariffs are not always easy to change over time, and that if you install a lot of distributed generation, maybe you will be trapped in a tariff signal that you have designed for previous levels of distributed renewables, and you will not maybe be able to make this tariff change over time?
Yeah, that's actually a very good question. It's something that especially Germany is grappling with, because there's so many studies that have come out in the past few years that tariffs there, the feed-in tariff system there is regressive and causing a lot of inefficiency. I would say that the main thing I would consider here is that the tariffs that we're assuming here, we're assuming that the tariff is the same during the entire time span of the solar panel installation. Now, we're doing this because we're making this choice because that's pretty much how most tariffs are designed. They're designed either to move, they're locked or constrained to move not at all, or move a very tiny amount over time, especially in the period in which these solar panels were installed. If we change this assumption and assume that solar panels would be, the tariff would change in some format in the coming years, the main thing it would do is it would impact the slope of the line, of the red line that I showed earlier in one of my earlier slides. And what that would do is, most likely is, as feed-in tariffs tend to decrease, it would simply decrease the slope of that line and make it less likely that a household would choose to install solar panels earlier on. Does that answer your question, Florian?
Yeah, thank you. Thank you.
Maybe I have a question that is a little bit outside what you do, but linked to what I'm doing. All these tariffs are, well, flat rates. We know the properties, but the other one, they can be quite complex. And is there any work that has been done with this type of tariff on the perception of consumer? Because at the end of the day, consumers may choose the tariff, and this can be quite complex because the use of their installation also, either as a producer or consumer, is complex. So is there any behavioral work that has been done on that to take into account the behaviors of consumers, prosumers?
So this is about the perception of consumers of different feed-in tariffs, right? Like flat tariffs and net metering and real-time pricing. Yeah, so there's actually some research that is done on this, but in my opinion, there's like, when we compare it to the research that's been done on the perception of consumers about consumption, about like regular electricity tariffs, the research is very, very weak. So it's very, I think there's a huge research gap in just studying the consumer perceptions towards net metering and flat rate tariffs and real-time pricing, but for generation assets. There's some discussion, there's some, let's say, perception studies that focus on more on investors, but I think they're kind of trying to answer a different question than the question that you see in those studies that are aligned towards consumption. They're kind of assuming slightly different populations. On the one hand, we have people who are kind of investors, active people, kind of financially savvy people. And on the other hand, we're assuming just the general population, and sometimes people who don't really think about their electricity until the end of the year. So I think there's a lot of work to be done there, unfortunately. Or maybe fortunately, because then we would know, we would have something to do.
Okay, is there any other question? Maybe I have one more. You study, so you base your study on a Texas data set, but you work at a European university. Are there things you can say about that, about the fact that maybe what you show in your paper must be somewhat adapted or qualified to be applied to European utilities, which are also very diverse, so maybe not all European utilities, but could you comment on this?
Yeah, that's a very good question. I was actually trying very hard to do this study in a region where you know, something like this will be discussed quite often, and in the US it's pretty good. It's also very good in Europe and in Australia. The main issue that I've been encountering is data availability. So in Austin, Texas, we have data that's available on a permanent basis, and we're talking good data. So data that doesn't necessarily, you don't see the smart meter disconnecting like 10% of the time. Now, I've tried to get this data from other places too, but unfortunately the quality wasn't as high. And that kind of made the conclusions a little bit difficult to compare. So we'd have to just kind of stick to extrapolating these results for other places. And I would say that the main thing that you would want to consider here is that, first of all, in many other places outside of the US and also in California, there's a very large difference between the price of electricity on the market and the retail price of electricity for mostly tax reasons. And this causes the results of this study to be vastly different. So in Texas, one thing that's very prominent is that, first of all, yes, there's a lot of solar generation because there's a lot of sun. But secondly, also the price of electricity on the retail market for a household is not that different from the price that they're getting back for selling their electricity. And that's mainly because of the low taxes that they have and other factors that are also low costs there. If we consider the prices they have there, which is like 11 or 12 cents per kilowatt hour, and compare it to, let's say, Germany, where you can easily find 30, 40 cents per kilowatt hour, it's really incomparable. That's why I think that it can be kind of hard to extrapolate these results to some countries in Europe and also California, and but it can also be easily extrapolated to, let's say, some regions of Australia and the rest of the US in the more sunny states in the south. Does that answer your question, Florian?
Yes.
Great.
We have a few more minutes. Are there any comments, questions, suggestions that you would like to offer? So I'll try a final one. So I had the impression from the abstract and when you presented today that you took a point of view on efficiency that was based on individual efficiency, if you can relate the cost or the willingness to pay of each customer toward the price of electricity or the signals you receive. Do you have any comment on the fact that maybe you could achieve collectively a better efficiency by distorting those signals and sometimes not sending incentives or signals that are right near the costs or the characteristics of the consumers, but for some a bit far away to achieve a better efficiency collectively?
Oh, I see. So if we can kind of send signals that are different from cost, because the efficiency point, like the actual value of electricity, might be different from what the cost would be, right?
Mm-hmm.
Yeah, so one thing I did here, which is something kind of new and something that I don't see done quite often in the literature, is that I also considered the value of clean electricity generation. So internalizing the external benefits, the externalities of clean electricity. That's something that's usually not done, and it's exactly because of this externality that many policymakers choose to price these feed-in tariffs at a price that is actually higher than what they should be. I mean, they're not crazy. They're not choosing to do this simply because they have some malice, but they're doing this because they know that these externalities exist. They guess that they are about a certain amount, and they try to price those feed-in tariffs so that they are closer to that. But indeed, if you don't include that as well, and you just consider the general market price and the general second value component about grid operations, and you compare the costs and find inefficiencies that way, you're going to reach a situation where you find a huge amount of inefficiency, and you're going to find a lot of room to complain about why it is so. Most studies do this. Most studies actually compare the results in this way, and I think that it is not necessarily an unfair way to compare it, but I would say, like, ever since 2 years ago, or sorry, it's been 3 years now. 3 years ago, in one of my papers, I sent in a paper and I got a comment from a reviewer in the Energy Journal, and he said that you really need to, when you're calculating efficiency like this, you really need to also internalize these externalities. And ever since then, I've been also doing that as well.
Thank you. Thank you. So I think we can wrap up on your paper. Thank you very much for this presentation and for answering our questions. And we will now move on to Carine Staropoli for a paper on the price complexity of electricity and water tariffs and some experiments with real consumers. Carine, the floor is yours.
So thank you very much, Florian, and thank you all for attending this session. So the paper I'm presenting is entitled "Giving Consumers Too Many Choices, a False Good Idea, a lab experiment on water and electricity tariff." So it was actually sent last year, and meanwhile it has been published in the European Journal of Law and Economics. And it's a paper that I've been working on and written with Alexandre Mayol, who is at the University of Florian. Okay, so what we do in this paper is basically try to compare what is happening in terms of tariff perception and also alignment of consumers' behavior in the case of electricity and water. So I will come back to the general context as an introduction. You all might know about electricity because we consider a very simple thing, but water, what is interesting also is the comparison that can be done with water. So if you look at what is happening in these two sectors in terms of competition and regulation, what we have in electricity is notably the retail market, the introduction of competition among the supplier, and the fact that nowadays consumer can choose among different type of supplier who offer different type of tariff in order to attract and contracts in order to attract consumer. In the water sector, at least in France, because we will do the experiment in France, and so we have in mind the French institutional context or regulation. It's more a competition for the market. That means that at the municipality level or intermunicipality level, consumers don't have the choice of the supplier. It's organized through competitive tendering. And once a supplier got the contract at the municipality level, consumers don't have the choice. So they have to take the supplier that has been chosen by the municipality. And the tariff also, they usually don't have the choice of the tariff. It's negotiated through the competitive tendering. But what is interesting is that they have tried to make a tariff system evolving in France and introduce notably increasing block tariff in the water sector. So that's something that we will deal with. In terms of technologies, both sectors are impacted with smart metering deployment. So in the electricity sector in France, we have the so-called dinky smart meter. In the water sector, the problematic is a little bit different because depending on whether you have an individual house, you can have a smart meter where you can have good information on your consumption and yeah, well, it's not and be able to control for better control for your consumption. When you are in a collective dwelling, it's not possible. Some of them, the tariff, the bill is really shared with the whole household in the collective dwelling. So it's also a bit different among the two sectors. And what is common in these two sectors is that they are really at the center of the ecological transition. And in both cases, the idea and the objective is to reduce consumption and to incentivize consumers to reduce their consumption through different manners, notably, as we will see, tariff, but also behaviors. So that means that many gestures can help to reduce consumption. So at the end of the day, when you look at this different aspects, what is the good news for, at least for economists, is that it becomes more and more possible, plausible, feasible to use the price signal. The famous price signal that Marcel Boiteux claimed was the only way to discipline consumer. It becomes feasible because of all these changes that we are facing in the electricity sector as well as in the law and the water sector. So our motivation was clearly to not oppose, but well, we start by observing that in theory, the properties of the tariffs, notably the dynamic tariffs, which are now feasible, and the price signal are quite clearly identified. Even if behavioral economics, I will come to that point later, insist on the fact that theoretical properties doesn't meet in practice. There are problems because in practice, notably, consumers don't perceive the tariff as they should perceive them because they are not as rational as the theory assumes they are, to make it simple and fast. And so the second question that we can see by stating this not opposition, but this distortion between theory and practice, is to ask the question whether consumers are able to align their behavior to the tariff. Notably, in our case, whether they are able to reduce consumption with regard to what the price signal send to them. So that's our research question. So the literature on this question, as we discussed in the previous presentation, is weak at the end when you're looking to answer to the precise question that we ask, because what we have, and for a long time, it's an already rich literature based on industrial organization contribution, since Co's contribution on the two-part tariff, notably, but also Tirole, Malin-Martimore, and so on, is that all the tariff that we consider, whether linear or non-linear, the simplest one we can imagine, notably flat rate, two-part tariff, and the most recent one that has been studied in the literature, the increasing block tariff, they each have some properties, good properties, efficiency properties, but no one satisfies simultaneously the what we could consider as a triptych, the fact that the tariff is supposed to cover the cost first, it's supposed to be efficient, and since we're talking about essential good, there are also questions of equity. And satisfying these three objectives is almost impossible for any type of tariff based on theoretical work. That means assuming that consumers are perfectly rational, which is far from being the case. And as a matter of fact, when you look at the literature, empirical literature based with real data or experimental data, when they compare two types of tariff, we find what are the different type of problems that occur in based on the or compared to the theoretical properties. And that's why we decided to use the literature on behavioral economics, and that aims at identifying the cognitive bias that can occur on the tariff choice first, on the perception of the tariff, how the complexity of the tariff, and so it refers to the cognitive bias, which is the aversion to complexity that has been studied in different situations, but also the complexity to align, as I have said before, the behavior to the tariff that you have chosen. So in total, this makes this question of cognitive bias very relevant, because we can see that it occurs at the two stages. First, when it's time to decide which tariff to choose, and then to adapt the behavior to the tariff. What we consider in this paper is the aversion to complexity cognitive bias. There are many other cognitive bias that have been identified in the literature, studied in the case of electricity tariff, notably the statu quo bias, which explain or help to explain why consumers don't switch to other supplier or other tariff as they should, because of risk aversion or loss aversion, which is also associated to this bias. So based on the literature that I don't develop, but we make three conjectures that we want to test in the lab. So the first one is that we assume a kind of how can I say it? We assume that, let's say, flat rate tariff remain more simple than two-part tariff and increasing block tariff in terms of understanding both in terms of perception first, and then understanding how to adapt the behavior to the chosen tariff. So we assume that the increasing order of complexity of tariff is first flat rate tariff, two-part tariff, and then increasing block tariff, which are the three tariffs that we will consider and test in the lab. So compared to what we have seen in the previous presentation, it is very standard and simple. It's the first step for us, but it's very interesting to see what we observe with the most simplest tariff we can imagine, compared to more complex one like net metering, which seems to be something more complex. So the conjecture we made regarding the aversion to complexity is first that spontaneously, so that means in the lab, I will explain what we mean by that, without incentive, participants prefer the simplest tariff. But when you start to incentivize them, that means to give them a monetary incentive if they choose the right tariff, that means the most advantageous tariff, the one that we propose them as more advantageous. And we explicit the price mechanism, that means we make the link between behaviors and price more explicit by giving them information on that. It helps to compensate the cognitive bias. That means it helps to reduce complexity. So that's what we want to test in the lab. And the third conjecture we want to test in the lab is based on this idea of comparing what happened with electricity and what happened with water in the same time. And normally, if a consumer is rational, he should choose a tariff for the tariff. And so that means that he should choose the same tariff, whether it's water or whether it's electricity. So there's no good effect. We shouldn't be able to observe a good effect. So for testing this conjecture, we conduct an experimental lab, an experiment in the lab, sorry. So we have recruited 237 participants. They were representative or pseudo-representative sample of water and electricity consumers in terms of age, gender, but also where they are living, whether an individual house or a collective dwelling, in Paris or in the suburb, and also in terms of professional activity, socioeconomic characteristics, let's put it this way. So we have run the experiment at the LEAP, the Laboratory of Experimental Economics in Paris 1, at the University of Paris 1. So the experiment is composed of 4 stages. I will introduce the different stages. And we conduct at the end of the experiment, which is quite standard, a risk aversion test, rationality test, and final qualitative survey based on stated preferences. So at the stage when they arrive for the experiment, we collect information on their consumption based on their equipment and the way they live and how many people in the household, etc., etc. In order to be able to provide them the information on how much kilowatt hour and how much meters cube they consume of water and electricity and water. That was important because one of the main characteristic is that usually people don't even know how much they consume. So then when you ask them to choose a tariff, they are already the fact is the choice is already based by the fact that they don't know exactly how much they consume. So we start by that, and then we have 3 stages. So the second stage consists in making them choose directly between 2 types of tariff, for water and for electricity. With that, we test the flat tariff, the 2-part tariff, and the increasing block tariff. And for that, we are able to determine whether they have a strict preference for one tariff for the water and for the electricity. Based on that, we provide them information on how they can, through their behavior, reduce their consumption of water and of electricity. So we take the usual gesture for water on one side and for electricity on the other. And we collect information on what is their willingness to adopt this type of behavior. So that means what they can expect to reduce in terms of kilowatt hour and megawatt and meters cube and the consequence for their bill. Okay, so of course it's in the lab, it lasts 1 hour, we are not able to observe what they really do, but at least we collect information on their willingness to adopt this behavior. And based on that, and that's the stage 4, we propose them the same choice of tariff, but knowing that if they do the effort, if they adapt their consumption, if they reduce their consumption, they can save money. And the objective is to see whether they change the tariff that they have chosen at the first stage. That means immediately through a perception. So that's the design of the experience. And of course, in that stage, there is one tariff that is more interesting for them, where they can make more saving in their bill, which is the more complex one. Okay, so we have defined the tariff so that they can make a saving if they adopt the more complex one. We do the final test that I have mentioned at the end. And I will present only two results. So the first one regarding the aversion for complexity, what we observe just at the level of descriptive statistic is that the more complex tariff, so the increasing block tariff, is the less chosen tariff, both for water, which is in orange, both for water and electricity. It's not the color. On orange is the first stage, and blue is the second stage, or the incentivized choice. And what we observe is that if we introduce incentives, so that means it makes the increasing block tariff should be more advantageous. We can see that it increased a little bit the choice of this type of tariff, the strict preference for this tariff, but it's quite marginal compared to the choice that they make in favor of linear tariff or two-part tariff in that case. So that means that as expected, consumer, both for water and for electricity, prefer simple tariff than complex tariff. And then we have a result for the good effect. And we measure that by observing incoherence of preferences. Typically, choosing a linear tariff for water, here, as you can see, it increases in probit model, regression model, it increases the probability to choose an increasing block tariff for electricity. So that means that the choice they make of tariff for one good, water, is not and is reversed than the one they make for electricity. And we observe the contrary for electricity. The probability to choose an increasing block tariff for water increase when they choose a linear tariff for electricity. So this incoherence is interpreted as a good effect. Sorry. And we observe that also when we incentivize the choice. That means when we reduce the complexity of the two tariffs. So in both cases, we observe a good effect. So this, as a conclusion, this experiment presents the first results based on one cognitive base, the aversion to complexity. Now that we want to focus on electricity tariff, we want to focus on notably the dynamic tariff. In the water sector, dynamic tariff doesn't make any sense, so we were not able to compare the two goods. So we are now extended our protocol, experimental protocol, to focus on different type of dynamic tariff. And maybe because it's also really a hot topic and in the agenda, typically the use of dynamic tariff in other sectors like sustainable mobility, with the use of mobility as a service application that will allow consumers to pay a real-time tariff also for the different mobility modes. So this is an exploratory work, I would say, that shows quite interesting and promising result based on simple things for the moment, but hopefully we will be able to extend it to other sectors and more complex tariffs. So thank you very much.
Thank you very much. Are there any questions from the room about this very interesting work?
Hi, yeah, I have a couple of questions.
Thank you.
Yeah, so thank you, Carine, for the presentation. It was very interesting. I have, first I was wondering, where can I find this paper? Has it been published already, or do you know when it will be published?
Yeah, it's published, and it's on the European Journal of Law and Economics. And well, I can, if you send me an email, I can send you the version just before publication version. I can send it to you.
Perfect, thank you. And my second question is, have you also considered doing a willingness to pay study on tariff complexity? Because has this been done before? Is there like already a willingness to pay study on tariff complexity?
Yeah, that's another type of methodology that can be done. For the moment, we are still in the progress of writing considering the extension of this work, and we might also do this type of thing. The problem is that with this type of topic, what you miss is to be able to control for some variable, notably the revenue and composition of the household, etc., etc. So that's why laboratory experiment is helpful to control for a number of variables. That you cannot gather using real data, especially in this field. Doing studies trying to evaluate the willingness to pay is also something that can be done to complete, I would say, this type of studies.
Yeah, I think it would be fascinating to have a lab experiment that would just give us like a disutility curve, if you will, for
exactly.
tariff complexity.
Exactly.
Thanks.
Thank you. Are there other questions?
Yeah, I would have also questions. Thanks for the presentation, Carine. I'm just wondering if you're able to control for statu quo bias in your study, meaning that probably the consumers know better the flat tariff than the more complex one. So do people that already are under flat tariff tends to stay on this, or on the same way, if users are already on something more dynamic, they are more keen to stay on something more dynamic?
Yeah, in terms of that's one of the questions that we need to address. We have not addressed that now, especially we can see that proposing tariff that doesn't mean that much to people like water consumers, those that have always paid fixed amount, part of the old charges that they pay when they are in a collective dwelling. When you ask them if you have to choose a tariff for water, what would you choose? Of course, you can imagine that they are lost. So the switching of tariff is something that really needs to be addressed, because basically that's what, and it's so through the statu quo tariff, to the statu quo base, or also through the framing effect, because of course, it's also a question of how you present the new tariff, the unknown tariff. It should be easy to control for the tariff they have and how they perceive another tariff depending on where they start with. So that's something that we might be able to introduce in the design, definitely, because that's one type of cognitive bias that has to be addressed regarding all these issues.
Okay, great. Thanks.
Thank you. We have still a few more minutes. I have a question, if I may. So actually, in theory, having more complex tariffs will lead you to a better efficiency. But then what you see in your study is that, in fact, consumers are not really driven by having a better cost sharing way, and are not really enthused by the fact that their tariffs might vary from time to time depending on their consumption. What is the most important thing to your mind? What do consumers really want more than the other? Is it having fixed tariffs? So are they really risk averse? Or is it they really want more to better share the cost, and so they are only the part of the cost that they really create? What is to your mind what drives this this choice for very simple tariffs? Is that they are really risk averse, or that they really don't care about better sharing costs?
So with this experiment, we cannot tell, because the risk aversion that we measure at the end, which was not significant as a control variable, we were not able to identify any correlation, any link between the choices. But that's a work that I had done before with some colleagues, Stéphane Robin and Valérie Lesgar from EDF and Ancamu, where we wanted to test much more diversity of tariff, much more complex, and notably real-time pricing with a problem of risk aversion. And clearly the aversion to fixed tariff was identified. So that's something that really need to be addressed, especially now that we also can test some solution, like proposing also complementary solution in addition to information, an explanation, information, etc., but also the possibility to be to use equipment that could control some consumption and reduce the part of risk, or the misalignment, or the bad adaptation of behavior with the tariff. So that's something that is part of the test that need to be done now, even in the lab, with this type of tariff.
Do you think the incentives people receive today are comparable or enough to trigger the choices that people in your lab face in the second part of the study? So if I'm not wrong, what you say is you just inform them that one tariff is better than the other, and they have the incentives that in the end they will receive a small payment depending on the choice they make. Today, as an electricity customer, for example, I think we all face these two. We all check these two situations. We will see our bill change depending on what we do, and we somehow are informed with ads and a lot of things that there is one tariff that is better than the other. Would you say that this is enough, or that we should do more to inform customers? What is the situation?
I would say that it should be enough, but it's already maybe too much. That means that, and that's quite problematic, because that means, of course, and that's one Carine in 2009, I think, was working on the obfuscation strategy by supplier. That means it was really a strategy to give a lot of information, real information, good information, but to make things even more complex, which at the end the consumer was not able to treat all this information and to take the best solution for him. So that's why the only solution would be to say to consumer, sorry, you're not rational enough or ready enough to deal with all this information, and you maybe should rely on some remote or control equipment that will help you to take the right decision. But then you have a consumer that will be reluctant to that because of loss of control, because of trust. Trust will be very important. And if you see what's happening now in terms of trust around all the green energy, is it green, not green, what do they tell us? And you can see how it starts to, and how people don't trust Linky, don't trust. So trust with perception will be the next issue to solve. And it definitely deals with cognitive bias. So that's why we are going to try to investigate some of these issues, not all together because it's a lot, but because there are different type of element that needs to be taken into account if you want to be close to what happened in the reality.
Okay, thank you very much.
Thank you all.
We have about 35 minutes left. Claudia, you can take control of the presentation, and the floor is yours.
Thanks a lot, Florian, and thanks for the other two presentations. I'm going to present a paper on prosumage of solar electricity, which I've written together with two colleagues of mine, Wolfgang Schill and Alexandre Zerrahn. And this paper is much inspired by the German context and the German tariff system, but I think many of the conclusions we've drawn can also be applied to other countries or other markets. So let me first start off with some background on why the German market is interesting, and I think this is something that most of you are familiar with. One thing that we've seen in Germany is that the average retail tariff, especially in the residential sector, has been strongly increasing in the past decade. And at the same time, the feed-in tariff for small-scale PV plants has been decreasing as the costs of PV have been falling. And this together means that we reached the point of grid parity around 2011, 2012, meaning that from that point on, it was attractive for owner of PV plants to consume part of their electricity themselves instead of feeding it into the grid. And this is a trend that we've been seeing and expect to continue to see in the future. In this paper, we thus take a closer look at prosumage, so at households that have a PV battery system and consume part of their PV's power themselves. They can also feed the power into the grid and store it with their battery storage. We are particularly interested in how the retail tariff and the feed-in tariff affect prosumage households' decision to invest into PV and battery systems, and what the impacts on the power sector are. We explore these questions with means of a numerical model, which I will introduce to you in a minute. So let's have a look at the model we worked with. So in general, the framework we chose is a mixed complementarity problem. This gives us the advantage to solve several optimization problems simultaneously. So here you can see part of the mixed complementarity problem on the left-hand side, which is a prosumage household. This household is representative for 1 million German households. It tries to minimize its electricity bill via the investment decision for solar PV and battery storage and the hourly dispatch of its equipment. The household sees different tariffs, both for its electricity consumption from the grid, but also for the power that it feeds into the grid, which stems from its solar PV plant. These tariffs we do vary within the different scenarios, and this is what we will have a look at later on. Besides the households that we have seen on the left-hand side, and we also do represent the power system, which is depicted here on the right-hand side. So we consider different wholesale generators and storage operators. The capacities of the power system are in line with the German network development plan, and there's a benevolent system operator which decides upon the optimal hourly dispatch. So this gives you the full picture of the optimization problem. In general, we try to consider all of the demand and generation of the German power system, And then, as I've said before, we vary the tariff scenarios. We vary the different tariff components within the scenarios depicted in red here. So let's have a look at the tariffs that we consider. This picture, I'm going to go over it very briefly. If you're interested in detail, you can have a look at it in the paper. This is just to give you an intuition how the feed-in tariff and the retail price lead to different incentive schemes for households. So in Germany, we started off in the situation in the left corner, A, where everybody was a pure consumer. Then there has been a huge feed-in tariff, which was introduced, meaning that households had an incentive to become full grid consumers, consuming all of their power from the grid and feeding all of the power that they produced into the grid. And then with the increasing retail price, we moved on to a prosumer era where it was and is profitable to partly consume your self-generated power. And in the increase in the future, and maybe for some households already, we are now reaching a prosumage area where the costs for storage are falling and the retail price is increasing, meaning that, yeah, we are in situation E or F, and the battery storage can be profitable. So these different schemes that we see here, we do try to represent with the tariff scenarios. The scenarios that we consider are listed here. In general, the scenarios that we do look at are supposed to represent Germany in 2030. The baseline scenario reflects the current situation regarding the tariff design. So the baseline scenario pretty much projects the current situation onto 2030. In panel 1, we then decrease the feed-in tariff. So in 2019, the feed-in tariff for small-scale plants was roughly 8 cents, and in panel 1, we decrease it down to 0, while keeping the retail tariff, which sums up to 30 cents, constant. In panel 2, we then vary the retail tariff by decreasing the volumetric part and increasing the fixed annual payment. We do this to make sure that the system costs are covered and to make the scenarios comparable between each other. So in all of the scenarios, we look at the pure consumers that do not invest into PV or battery storage are left off the same. Lastly, in the scenarios of panel 3, we introduce real-time pricing both for the power feed-in and the power consumption. So let's have a look at some of the results. These graphs here show the optimal capacities for households for each of the scenarios. The gray bar represents the PV capacity and the black dots are the optimal storage energy capacity. What we see when looking at panel 1 on the left side is that when we are decreasing the feed-in tariff from 8 cents down to 0, the optimal PV capacity decreases, as the PV capacity, when the FIT is below the LCOE, is aimed at optimizing self-consumption. The battery storage, however, is rather robust with respect to the feed-in tariff and doesn't really decrease that much. Instead, the battery storage is much more sensitive to the retail tariff. This is what we see when we look at panel 2, where we vary the retail tariff. And this is due to the fact that, yeah, the storage investment are governed by the difference between the retail tariff and the feed-in tariff, since this is pretty much the offsetting margin for the household. We also looked at the electricity bill and what those tariff means for the households. In general, we see what I think one would expect in any case is that a high feed-in tariff induces a shift from the costs for power consumption from the grid towards investment into PV and battery storage. With higher fixed part in retail tariffs, we do see that the cost-saving potential of Prosumage decreases a lot. When we have very high fixed parts and low volumetric prices, households do not invest into battery storage, and thus their saving potential is quite low. One interesting policy that we also looked at, which you can see at the right corner of the first panel on the left-hand side, is the feed-in cap. So households there are only allowed to feed in a maximum of 50% of their power, of their peak PV capacity into the grid. And as you can see when comparing the black cross with the baseline, which is the second bar, is that this policy has minor effects on profits. Besides this households perspective, we also looked at some indicators with respect to the power system. One that is shown here is the peak demand and peak feed-in into the grid. So we can see here the residual load duration curve for Prosumage households. What we found is none of the investigated tariff schemes help to reduce the peak grid demand. So you can see this when looking at the left-hand side of each of the panels. The peak demand doesn't really change just because the battery storage is not large enough to accommodate enough energy to transfer this into the hours where households have very high demand. But what we do find is that the feed-in cap policy and retail pricing helps to lower the peak feed-in. So this is what you can see on the right-hand side, where some of the maximum feed-in is considerably lower compared to the reference case. Last, one interesting trade-off that we looked at is the trade-off between the PV capacity and the cost recovery of Prosumage households. This is a trade-off that is especially relevant for Germany, but I think this is an issue in many countries with large PV capacities. So what we do see here, for example, on the left corner, is that the pure consumers, they contribute with more than 1,200 euros annually to the recovery of fixed system costs, like, for example, network fees, while the households that invest into PV and battery storage, when we have higher feed-in tariffs, they do contribute a lot lower. So in a scenario with a retail price of 30 cents and a feed-in tariff of 8 cents, households contribute a bit more than 200 euros annually to system costs, but provide a PV capacity of 10 kilowatt peak. One combination that we found interesting regarding this trade-off is that a high feed-in tariff and the dominant fixed part in retail tariff performs best in this regard. So in the middle graph on the right-hand side, we do see Prosumage households that provide 10 kilowatt of PV capacity, but at the same time contribute considerably to fixed system cost recovery. So summing up, what we found is that the incentives set through power pricing, consumption, and the feed-in tariffs are fundamentally different. While the feed-in tariff strongly impacts the optimal PV capacity, the battery is not much affected by the feed-in tariff itself. Instead, it's those high volumetric retail tariffs that drive the profitability of batteries. Regarding the effect of Prosumage on the power system itself, we found that it really depends on the tariff system, and this is what policymakers should keep in mind when designing the tariff system. None of the tariff designs that we investigated clearly dominates in all of the system indicators that we looked at, and it's something that we've heard before already in the presentation, that it's probably impossible to find a perfect tariff design. What we found, however, is that the high feed-in tariff together with high fixed part can address this trade-off between providing high PV capacity, but also recovering the fixed system costs. Besides, we found that the feed-in policy can be quite useful because it helps to reduce peak feed-in to the grid without causing major distortion for the prosumage households. And regarding the modeling setup, we found that this mixed complementarity problem is quite useful to study the effects of prosumage, because you can easily reformulate existing problems and simulate tariff scenarios with real-time pricing options. And with this, I would like to close. The paper has been published quite recently in open access in energy policy, so feel free to have a look at it. And with this, I would like to open the floor to questions.
Thank you very much. Are there any questions from the room, either through the chat or the video? Okay, maybe I start with one question. So you show very different levels of contributions of consumers towards system fixed cost, depending on the tariffs they face. Do you have any idea of how those contributions compare to their fair share of those costs? Meaning the full consumer has a very high contribution to fixed cost, the other are lower or very low, or depending on the tariff. Are they in proportion to the fixed cost they should compensate for, or is it totally different? Do we have a death spiral problem or not?
Yes, let me maybe go back to this slide. So of course, the question is what is their fair share? So in Germany, the way that we pay our electricity bills is that the network fees are also measured on a volumetric basis. And this is, of course, it's arguable whether this is fair or not. It might make more sense for everybody to pay a fixed annual share or not. Regarding the fixed system cost, I would argue that if you look at, for example, the left panel there, prosumage households definitely do not provide their fixed share regarding network costs. So in the extreme case, for example, they pay only about 250 euro or so. And this is, of course, a huge equity problem, because pure consumers, which might not be able to afford solar PV, contribute a lot more. But at the same time, those households do provide solar PV capacity, and they might even help to stabilize the distribution grid if the right policy incentives are in place. So I guess it's hard to say, because you would really have to think in detail about what is the fair share in system costs.
Thank you.
I would have a question also. Thanks for the presentation. I'm just referring to, I think it was slide 12, where we can see that the retail 30 feet 8 is actually lower the bill for the consumer. So it would basically mean that it's already interesting, or was interesting in 2008 to invest in PV and storage for consumers, because if I understand correctly, that's the current situation in panel 1. So is that the case?
So yeah, I might have explained this not so well. So the current tariff scheme is projected onto 2030. So with current, I mean the situation from 2019, but of course the costs for PV and storage are assumed to decrease. So it's not exactly the same situation, it's just the current tariff schemes and future costs. So in 2019, for most consumers, yes, a PV battery system with this high feed-in tariff was attractive, but not the storage system without subsidy. So in Germany, we used to have this KfW loan. And this is why we have seen a lot of storage being built together with the PV plants. And this is what made it attractive in 2019.
Okay, interesting. And just on panel 2 here, we can see that bill increases in the first 3 cases compared to a pure consumer scenario. And I'm just wondering if your model still triggers some investments because there are some, I don't know, some side benefits to have such investments, or how come that you might have, or maybe it's it's remuneration for feed-in that compensate the difference.
Yes, so the total annual electricity expenditure is the black cross. And if you compare this to the pure consumer on the left-hand side, you see that they still have a lower annual bill because they invest into PV and storage. And yeah, I think that makes sense, because if it wasn't attractive, then they would stay pure consumers and decide not to invest. And so they're offsetting some of these additional costs that we see when looking at the positive bars with the remuneration for the feed-in tariff.
Okay. Thanks.
You're welcome.
Thank you. Please feel free to ask more questions or to ask questions that might find appropriate.
I have a question.
Yes.
Claudia, thanks for the presentation. I have a more general question, if you will. Basically, if you were a policymaker in Germany and given the expected changes in price for solar panels and for lithium-ion batteries, how would you, what price would you set on the feed-in tariff and also for the retail price? What would you do with these two things?
Yes, so what I would do is have a look maybe at this graph, and there you can pretty much think about, okay, what world do we want to be in? Do we want households to only install solar PV, or do we want to install them PV and battery storage? And depending on that, we could pick the optimal combination between the feed-in tariff and the retail tariff. Assuming that we would want households to install both solar PV and battery storage, because in theory the battery storage could be used in a sensible way for the system, then yeah, I would argue for a feed-in tariff and a retail price combination in that gives us this field F, where we have the highest PV capacity possible, because we do need a lot of PV capacity in Germany to reach carbon neutrality. Yeah, does this answer your question?
Well, my question is, let's say, a little bit more pragmatic. So considering the current level of fit, right, and the current retail price, let's say in a region like, let's say North Rhine-Westphalia, what would you do? What would you prefer to see? Do you think the retail price should be higher? Do you think that the fit should be lower, or vice versa?
So I think what's important is that the feed-in tariff stays in place in the first place, because this is something that has been discussed in Germany, and I guess the question then is, should it remain at a level that is comparable to today, where it's oriented roughly at the levelized cost of electricity or not? And I guess that's a fair level. What I think we do need to revise is the retail tariff and its design, because at the current level it doesn't really give the right incentives, and it's not provoking any system-oriented behavior from households.
Okay, thanks.
Thank you. We have about 5 to 10 minutes more. Maybe I have one question. So in your MCP, you have on the left side, so on the consumer side, just financial incentives to install PVs and batteries. Are there any other incentives you would like to, you would like to include in this model regarding the incentives provided to consumers to install PVs? And would that change your conclusions or the equation?
What kind of incentives do you have in mind?
Well, I have in mind, for example, the regional subsidies that can take different forms, being payments, being facilities to install the PVs, being reduction somewhere else, or different kinds of incentives that are not directly feed-in tariffs or retail price linked, and also words of mouth. For example, when you see that in some places PV is developing fast because some neighbors have installed first the PVs, and in others where the feed-in tariffs or retail price are exactly the same, there is no PV at all, just because there hasn't been kind of a movement, a drive to install those. So for example, those kind of things.
Yeah, it's a very good question, and I think it points towards the limitation of our model. It would be easy to implement, let's say, a lump sum payment or a subsidy for cost of PV or battery storage. That wouldn't really change the result that much. But I guess one of the weaknesses is that we purely base this on economics. And I guess it's fair to say that households are not fully rational, and they don't calculate towards each cent of their electricity bill, and there are a lot of other factors that we simply cannot represent. And yeah, I think it would be hard to implement those soft factors into our model. Yeah, but yeah, it would be nice if we could.
I think Carine mentioned the trust that would be needed if we wanted to have more complex tariffs be efficient. Is there also a trust issue there? Because in the model, everything is known in advance. So you have consumers that know that the feed-in tariffs or the retail prices are those, and they can take an investment decision based on this. I think it's not the case in reality, because those tariffs change. Sometimes you are not guaranteed a tariff for a longer period. What does that say about this role of developing PV, or what you see in your model?
Yes, well, I think regarding the tariff option that we have looked at, there's not such a huge trust issue. So in Germany, the feed-in tariff has been in place for so long. It's been working very well, and I think households do have a lot of trust into this. And if you continue to pay feed-in tariff to households, then even if they cannot offset as much electricity as they expected to, or if the retail price decreases, they still have this feed-in tariff for, let's say, 20 years. So they have a lower bound regarding the profitability. So yeah, I think in that sense, trust is not a big issue. But of course, this would change when you look into more innovative retail pricing schemes, because people simply do not have much experience with this.
Okay.
I would have an additional question, if possible. So I think in your model, you've considered like pure storage capacity. So just a battery that is more or less always available and is able to arbitrate on the dispatch. I'm just wondering if you would have the opportunity to replace this by more electric vehicles that therefore wouldn't be able to make the arbitrage each hour because you would use your car basically, and to what extent this could have an impact on the results. I don't know if you plans to test this or if you would have some ideas about it.
Yes, yeah, that's an excellent question. This is something that we're thinking about now and an extension that we want to consider. We haven't modeled it yet, and I think we would consider it additionally, not change the electric vehicle for the battery storage, but just add the electric vehicle to the household demand. And this will, of course, really make the analysis much more complex.
Interesting. Thanks.
I have a question.
Yes, please.
Yes. In terms of in the 2030 timeframe, how are the feed-in tariffs in Germany set? So what drives, is it a policy outcome that sets the feed-in tariff? Is it a time-weighted average price of solar PV in the market? So yeah, just seeing in terms of, is it a policy outcome or is it a market-driven price that's being incentivizing FITs?
You ask about the feed-in tariff, right?
Correct.
Yes. Yeah. So in the past, it's been oriented at the levelized cost of electricity. So in the beginning, it was the LCOE and then a big markup. Now it's roughly at the point of the LCOE. And in the future, I think it's up to see. So for the next years, it's quite clear that it still will be in place, but the new EEG that came out last year said Germany would revise its feed-in tariff schemes and potentially phase it out by 2027. So it could be at zero by 2030.
Okay, so that means you end up in, I guess, region E.
Let me take a look myself to not confuse. Yes, exactly.
Okay, thank you.
Okay, if there are not any more questions, thank you very much to our three speakers for their work and their presentation, and thank you to all the participants for their questions and their participation. And I wish to see you in other sessions of this conference.
Okay, thank you everyone for attending the session. I hope you all we had a nice time together, and enjoy the rest of the conference. Bye.
Thank you. Bye-bye.
Bye.
Bye.
Thank you very much for the help, and good luck for the rest of the conference.
Thank you. Bye.
Bye.